Hello, my name is Awadelrahman Ahmed. I'm a PhD student at the University of Oslo, the Department of Informatics. My research focus is on machine learning applications on smart grids and energy markets. Primarily, I am working around generative adversarial networks applications on one hand, and trying to combine machine learning and combinatorial optimization on another hand. In the next 30 minutes, I am intending to share an empirical study that aim to give some intuition about using transfer learning by parameter sharing in the context of generative adversarial networks. In fact, at some point in my research, I needed to apply transfer learning to some GAN-based models that I developed. And it turned out that applying transfer learning to GANs is not as intuitive as the one can think. So I had to run a series of experiments to figure out the best way to transfer the learned models. Those experiments were in our application domain, where we mainly deal with time series data. Then, after getting some results, I was curious about if those results can be extended to other fields, particularly GAN's applications on images. So in this talk, I will go through those experiments, and hopefully I will convey some results at the end. I'm planning to give my presentation in 4 parts. I will start by giving a very brief introduction about generative adversarial networks and transfer learning. Then I will introduce our application domain problem, the load disaggregation, and how GAN's framework is able to solve this problem compared to other methods. I will show how we apply transfer learning to GANs for this particular problem. Then on the images data, I will show the results on the image-to-image translation problem. Lastly, I will end with some concluding takeaways. I am pretty sure that many of you have already worked with generative adversarial networks, but very briefly, we can say that GANs is a deep learning generative framework which can produce realistic looking data from noise. GANs has tremendous applications in computer vision, where there is a need to synthesize images, and also it has many other applications in other domains. A GAN learns to generate data that looks realistic with the help of 2 networks, as shown in this figure. A generated G that takes a random noise vector Z and generates a data sample G of Z. The second network is the discriminator D, which has the access to the real data X, and its task is to classify if those samples G of Z are real or not. Based on the discriminator output, both networks are updated in an adversarial way, meaning that the generator aims to minimize the same objective which the discriminator aims to maximize. Through training, the generator will be able to learn to produce samples that look more realistic and good enough to fool the discriminator. After successful training, the generator will be able to arbitrarily generate data samples that are similar to our real ones. GANs have many variations. One flavor of GAN, which is related to our today's presentation, is the conditional GAN, which tries to condition or control the produced output on some input instead of arbitrarily producing samples randomly. This condition can be represented by vector C on the input side, as shown in this slide as label C. The other important concept to introduce is the transfer learning itself. There are many ways to realize transfer learning in the literature, but here I am particularly referring to transfer learning by parameter sharing. and it is a working solution for the case where we want to work on a domain that has limited data, like classifying scarce animals, such as the one in the bottom picture, which I have never pronounced its name correctly before, but I think it's Trazier. But we do not have enough training data of that Trazier or Tarsier, as it is already rare and scarce in nature. But luckily, this animal has some common features with other animals that have plentiful data, such as cats. It turned out that if we train model on cats' images for classification purpose, the first layers of that model learn generic features that are common between animals. And it can be useful if we transfer them, or those learned features, those common features, to our model, which will be trained on the target domain. Whereas the last layers can learn specific domain features that are very descriptive to the source domain, and we must retrain them on the target domain. So the usual way to transfer learning by parameter sharing starts by training a model on the plentiful data of the source domain, then transfer the first layer parameters and initialize the last layers, and retrain the transferred model on the limited target data. In this presentation, we want to see mainly how this looks like in GAN setting. And as you might remember from the previous slide, that the GAN has two networks rather than only one network. So at this point, let me firstly and very briefly introduce our specific domain or specific problem that we originally wanted to solve in the energy field, and what is called load disaggregation, or the long name is non-intrusive load monitoring, or for short is called the NILM. And this sophisticated name is simply a system that takes only one measurement that represents the total electricity consumption of a building as an input, and tries to figure out which appliance is on or off in that building at each time step. So the input to the NILM system, for example, is going to be smart meter measurement, and the output is the breakdown information of the appliance consumption. Why do we want to do that? Actually, giving this detailed feedback encourages the consumers to make energy savings and use energy efficiently. Talking numbers, those savings were quantified by some research to be up to 12%, which sounds motivating to spend some time solving the NILM problem. How do developers of NILM solve it so far? Actually, there are two main paths in the literature, either by using optimization, trying to find appliance combination that minimizes the difference from the total measurement, or taking the second and promising recent path, which is using pattern recognition and machine learning methods. Now, how this NILM problem is related to our discussion today about transfer learning and GANs is that we developed GAN-based models that solve NILM problem, which outperform the state of the art. And we wanted to achieve some level of generalizability of those GAN-based models, in the sense that the NILM system provider can use the same model as much as possible when shifting from one domain to another. For example, moving from one country and want to deploy those NILM systems in another country. Transfer learning was one of our approaches to achieve this level of generalizability, and more details about this specific work is on this paper, but I'm going to capture the related results in this presentation. Basically, thinking about NILM as a pattern recognition problem comes from the observation that individual appliances have some specific signature that is reflected on the aggregate measurement. As on those two figures, the orange plots are the smart meter reading, which is the total consumption of the building, and the blue plots are the individual consumption of the washing machine on the left and the dishwasher on the right. And you can see that the total measurement reflects or has some common features or common patterns between the total between the total measurement and the appliance measurement. To solve NILM, we actually built our models based on GAN's framework. Our GAN NILM generator takes an input as the smart meter measurement and tries to generate an appliance level measurement. This generated appliance is introduced to a discriminator, which has the access to the appliance ground truth and tries to figure out if this generated sample is real or not. Through time, the generator becomes better in producing appliance level measurements only from seeing the smart meter measurement. And the discriminator gains experience in classifying those better samples from the real ones. And both networks learn through time. To make GANs work for NILM, we had to do some adaptations to the loss function, but the adversarial notion was that we discussed just in the previous slides is still the main scheme of training. Actually, when we evaluated GAN NILM on the same building, we outperformed other models based on convolution neural networks and autoencoders. But the interesting practical question we addressed further is the case where the NILM system provider has trained models on some buildings and want to use them to disaggregate other buildings. This is practical because collecting appliance level training data is expensive and cannot be available for every building. Think about a company that train models on buildings in Oslo and wants to deploy in New York City. And then our question is going to be to what extent Oslo models can be used in New York City. Transfer learning by parameter sharing can solve this, but we have to figure out how to apply it on the GAN setting, since now we have two networks instead of one, and we do not intuitively, we cannot intuitively tell which network and which part of that network holds the generic feature to transfer and which hold the specific features that we have to retrain. Also, we can perform the retraining by either fine-tuning the transfer parameters or freezing them. So there are many options. And to explore those options, we conducted a series of experiments following this procedure. First, we start by training a GAN NILM model, M, on the source domain data. And then we progressively transfer G number of layers of the generator network and D number of layers of the discriminator network and initialize the rest of the parameters. Then we retrain this modified model on the target domain data, which is limited, one time by fine-tuning and another time by freezing the parameters. Each combination of these options produces a retrained model, M star, for which we calculated the performance on the target data based on F1 score. The source and target domains can be the electricity consumption of two different buildings from the same dataset, or from different datasets, or even different countries. We used the For that, we use open access datasets, the benchmarking dataset that is commonly used in the NILM field. Actually, this procedure produces 70 M-star models for every source and target pair, as we have 5 discriminator layers and 7 generator layers in the structure of GAN-NILM. And we did this by either fine-tuning or freezing the transfer parameters. Now, before I show the results, I am just going to explain what is going to be, what is expected to see. So on those two figures, the x-axis will show the index of the layer until which we transfer the parameters, and after which we initialize them. The y-axis will show the F1 score of the transferred model M star on the target data. The left figure will show the F1 score from the discriminated perspective, and the right figure will show the F1 score from the generated perspective. For example, on the left figure, on index 1 of the x-axis, we will plot the average F1 score across all models in which we transferred up to layer 1 of the discriminator, regardless to the generator layer. And on index 3 of the x-axis of the same left figure, we will plot the average F1 score across all models in which we transferred up to layer 3 of the discriminator, regardless to the generator layer. Similarly, on the right figure, on index 5 from the generator perspective of the x-axis, index 5, we will plot the average F1 score across all models in which we transferred up to layer 5 on the generator, regardless to the discriminator layer. So on the discriminator figure, this red plot shows the case of freezing the parameters when being transferred, and tells us that the more layers we transfer from the discriminator, the less the performance will be on the target domain. And we can infer from this that discriminator holds specific domain features. That means the best choice to do for the discriminator is to transfer as few layers as possible from it. And if we transfer the whole discriminator, for example, up to layer 5, this will lead to a very low F1 score on the target domain. From the generator perspective, the right figure shows the performance seems to be stable with the best value when transferring the whole generator, which is somehow an indication of that the generator mostly holds generic and common features between the two domains. When fine-tuning, the plots are shifted to higher performance values, as on those yellow plots, and but still following the same trend. I mean, we can still say that the more layers we transfer from the discriminator, the less the performance will be. And the more layers we transfer from the generator, the higher the possibility to get better performance on the target domain. From this, and on this particular NILM problem, we decided to select our best transferring option by transferring the whole generator network and start with a fresh discriminator network on the target domain. Now, the sensible question is if this can extend to other domains than time series data. For that, we investigated the image-to-image translation as one of the successful applications of GANs. Image-to-image translation examples can be producing maps from aerial images or photos from edge sketches. And the generator output in this application is conditioned by the input image, and it tries to produce a corresponding image that is similar to some real data, and the discriminator has the classification task that we have already been mentioning all the time, and this can be thought as a conditional GAN setting that we discussed earlier. One of the successful image-to-image GAN architecture is the one designed on this paper, and it's relevant to our results to say that the generator in this architecture has a bottleneck-like architecture, and it has skip connections. Using skip connections means that some layers receive additional inputs from layers other than the ones just before them. And actually our results show that skip connections have an effect on how the generator learns generic features. And we will do the experiments with two settings, one with skip connections and one without skip connections. Now we follow the same procedure we showed earlier. We choose two domains that we want to transfer between, a model that learns from mapping bags sketches to bags images, and as the source domain. And our target is to map between shoes sketches and shoes images. You might see that there are some similarity on the problem context, but the items are different. This similarity between the source and target domain is fundamental for successful transfer learning. Without introducing skip connections, we have a pretty similar trends as before, meaning that the more layers we transfer from the discriminator, the less the performance we will get on the target domain. And we can still infer that the discriminator holds specific domain features. On the generator side, the more layers we add, the higher the performance based on the structural similarity SSIM index as a metric. And the more layers we add, the higher the performance on the target data we get. And this reflects that the generator still generate common features between the source and the target domains. And the option of transfer learning, of transferring the whole generator and starting with a fresh discriminator with fine-tuning on the target domain is still the best way to transfer GAN's model from these images data. However, when introducing skip connections, the generated trend changes from that increasingly well performing by adding more layers from the source domain to having this V shape. And actually, this can be explained by being a direct effect of the skip connections, which force the layers to learn features in a collective way, meaning that the first layer learns of the generator learns common features collectively with the last layer, and so on. And the generic features that learned by a layer cannot be effective until it's complemented by the layer that is connected to. But still the best performance is when transferring the whole generator. I didn't show the discriminator perspective plot because it goes the same way that we have seen earlier. Well, if there is a conclusion for this presentation, is going to be that we show the procedure to apply transfer learning to GANs, as we showed empirically that the generator tends to hold generic features and the discriminator tends to hold specific features. We showed this in two application domains, time series with our low disaggregation problem, and on images on the image-to-image translation problem. Actually, this result goes hand in hand with the theoretical fact that the discriminator actually learns an implicit loss function that makes it able to differentiate fake samples from real samples. The important takeaway from this is if it happened to need to transfer GAN-based models, we should start by fresh discriminator and transfer the whole generator from the source domain as our first potential best option for transfer. This is the end of my presentation. I'm happy to receive questions and comments, and thank you very much.